Hello and welcome to this guide on electrical power. At its heart, the concept is quite simple. When we talk about electrical power, we're talking about how fast electrical energy is being used or moved from one place to another. Imagine you're using a garden hose. The total amount of water you've collected in a bucket is like energy. But the speed at which the water is gushing out of the hose, how much water comes out every second, that's the power. So, electrical power is simply a measure of how much work electricity is doing for us in any given moment, like lighting up a room or heating our food. Now, let's look at the language of electricity, the basic formulas. The most fundamental formula you'll ever see for power is P equals V times I. Let's decode this. P is for power, which we measure in a unit called watts, abbreviated as W, named after the inventor James Watt. When you see a 60-watt light bulb, that number is telling you its power consumption rate. V is for voltage, which we measure in volts. Think of voltage as the electrical pressure or push in a circuit. Going back to our hose analogy, voltage is like the water pressure from the tap. The higher the pressure, the more forcefully the water is pushed through the hose. I is for current, measured in amperes, often just called amps. Current is the actual flow of electricity, the volume of electrons moving past a point per second. In our analogy, this is the amount of water flowing through the hose. So, the formula P equals V times I tells us that the total power is a product of the electrical pressure, voltage, and the electrical flow, current. You'll also see two other related formulas, P equals I squared times R, and P equals V squared divided by R. These aren't new laws, they're just clever combinations of our main power formula with another rule called Ohm's law. They introduce a new term, R for resistance, measured in ohms. Resistance is anything that tries to slow down the flow of current. It's like pinching the garden hose, it resists the flow of water. These alternative formulas are useful when you know the resistance of a component but might be missing the voltage or the current. Finally, the image shows that power can also be defined as work done per unit time, or P equals W divided by T. This beautifully ties back to our initial definition. Power is the rate at which work or energy is used over time. Next up, let's talk about the two main flavors of electricity, the types of electrical power. First, we have DC power, which stands for direct current. This is the simpler of the two. In DC, the electricity flows in one steady, continuous direction, and the voltage remains constant. This is the type of power you get from batteries and solar cells. It's like a river flowing smoothly in one direction. The second type, which powers our homes and cities, is AC power, or alternating current. As the name suggests, the current doesn't flow in one direction. Instead, it rapidly alternates, flowing back and forth many times per second. The voltage also continuously rises and falls in a wave-like pattern. This is the power we get from power grids. Because AC voltage is constantly changing, we use special effective values called RMS, which stands for root mean square, to calculate its power. The formula is a bit more complex. P equals VRMS times IRMS times the cosine of phi. That last part, the cosine of phi, is called the power factor, and it's a correction that accounts for how well aligned the voltage and current waves are. For a simple device like a heater, they are perfectly aligned and this factor is 1, but for motors, it can be less. Finally, because the amount of power we use can vary enormously, from a tiny computer chip to an entire city, we use a system of prefixes. This table helps us talk about these vast differences without using a ton of zeros. We start small with the nanowatt, which is a billionth of a watt, and move up to the microwatt and milliwatt for small electronics. Then we have our standard watt. For bigger things, we use kilowatt, which is 1,000 watts. Your oven might use a few kilowatts. A megawatt is 1,000,000 watts, enough to power a small town, and a gigawatt is 1,000,000,000 watts, the kind of power produced by a very large power plant. These prefixes make it much easier to express the scale of electrical power all around us.